Hi, Darwin, and hi, Jack.
Hi, Jack.
How are you? All right. So, hopefully we saw some cool connections between the graph of the original and the graph of its derivative. What do you guys know about, or what did you guys notice about the power?
There's always one less.
Now only one man
The
can have
derivative
it.
always has one less. Very good.
That no one man should have.
What did you guys notice about the one where it was like a linear function and its slope was going down? What was the equation of its derivative?
Negative.
Y equals the negative value, right? So it's under the x-axis. All right. And then I feel like those were like probably the two big patterns you guys saw while you were trying to figure it out, right? Did anyone notice anything else that was really cool that you want to mention, or was it like that's pretty?
The greatness decreases.
He's pretty Gucci. You heard that. Okay.
Yeah.
All right. So let's begin by thinking of a way that we could do this so it's the same every time. An algorithm, if you will. Okay. The what?
The degree decreases by 1.
The degree is going to decrease by 1. So let's begin by classifying the original so we know what its derivative is going to look like. Here's what I mean. So in activity 1, which is a lie because we just did activity 1, page 23. We're on page 23. The pages could have changed though because I think this is an old one. Are you on page 23?
Yeah.
Is this the right page? Okay, we are on page 23.
Yeah.
23. That's like
2-3.
Yeah, no.
Page
We got
21 is not good to page 20.
Let's look at question 2. What are you given, the graph of the original or the derivative in question 2? The derivative. Good job. There's an F prime here. So if I'm examining the derivative, right, here's what I need in order to figure out what's happening in the original. So first of all, what is this guy? I'm looking for linear, quadratic, cubic. This is quadratic. Okay. So that means its original is going to be what? Cubic. Okay. Perfect. So I've got that going. Now, when we've been dealing with first derivatives in the past, what did we always write to contextualize what's happening in the original? What did we always draw?
What?
When we were examining the first derivative, what did we always draw to get information about the original? A number line. Okay, so let's think. I was too scared to say. Let's think about what kind of key information pieces are on the number line, right?
Thank you.
We do look for where the derivative is equal to 0, right? Those become the tick marks on the number line, right? So where's the derivative equal to 0? They're going to be at the x-intercepts, at the zeros. Good job. So let's label our number line because that's what we always do. And the derivative is equal to 0 at -2 and 2. And these were zeros. These were not undefined. These were zeros. So now pick up your highlighters that you got. I was hoping that you could do like pink is red and green is green. Green is positive. Because you guys don't have red highlighters. You know what I mean? You need one that's negative and one that's positive. So just write at the top of your paper what you selected, okay? So this is going to be positive for me. This is negative for me. What? What do you mean a split?
It's like split down the middle.
What if there's someone bites them?
So now someone's making 2 lines. Look at that. Now it's
It's
making
got a
2
middle
lines.
part.
No, we had this game. You guys ever play the game that comes with foam burritos? What is it called? There's like a foam burrito. Yeah. So like me and my whole like side of the family, we had a summer house and we went to Rhode Island. And someone had taken several bites out of the foam burrito and no one would fess up. And we still don't know who did it. Anyway, very strange. So, when you are testing on the first derivative number line, you are examining the outputs of the first derivative with the given test values, right? So to the left of -2, what are the outputs of this derivative? Positive or negative? Positive, right? It's positive on that whole side. So let's do a little positive here. Then, what does the sign or the output of the first derivative become between -2 and 2? Negative. Change to your negative color.
Oh, we had
Then, this is a lot of changing of the markers here. Okay. Then we are going to look at the next one, which is 2 to infinity. What's he? Positive. Okay. What else do we do on the first derivative number line? We classify where there are maxes or mins, right? So look at your first derivative line. Let's see. I've got a max at -2. And then at +2, I have a min. Okay. So this is pretty cool. Like from the first derivative number line, I can sketch the original now, right?
Yeah.
So I know that I've got a max at -2.
Yeah.
Right?
Yeah.
Yeah.
I know I've got a min at 2.
Oh yeah.
Can it be here, or does it matter? Or can it be here?
It could be anywhere.
It could be anywhere, right?
Yeah.
To the left, the original graph is increasing because the first derivative is positive. In between -2 and 2, the original graph is decreasing because it's negative.
Yeah.
From 2 to infinity, the original graph is increasing because the first derivative is positive.
Yeah.
You did it. Okay. Now, think about why. No, the best example is probably in the next one. Okay, I'll show you the next one. So, how are we feeling for the next one? Let's classify the derivative. The graph of the derivative, what is he? He's linear. And then Jason, what are you telling me about -3? Because it feels important. It's a 0. Good job. And then to the left of -3, what are the outputs of the derivative function? Literally negative. And then to the right, what are the outputs of the derivative function? Definitely positive. So what is -3 on the original graph? We go from decreasing to increasing. It's a min. If the derivative is linear, the original is quadratic. There is a minimum at -3. Is this guy facing up or facing down? How'd you know?
Yeah.
Oh, yeah, good job. You could think about it too. That's a good way to think about it. All right, cool. I was just going to say because it has a minimum. If it had a maximum, it was facing down, but that's even better. Good answer. So, now, here's what I want you to think about. Why does it not matter where I put the minimum as long as it's a minimum and it's quadratic? Let's say I had a graph that looks like this. Is he still quadratic?
Yeah.
Does he still have a minimum at -3?
Yeah.
What would be the only difference between this guy? This is the one in black, right? And then what about the one I just drew for purposes of argument? Maybe, could it be that?
Yeah.
What happens when I take the derivative of this guy? What happens to all the constants?
They're different.
They disappear, right? So if the vertical shift is the only thing that's affecting where the minimum and the maximum are located, as long as it's the right kind of function, doesn't really matter, right? It's just a sketch of the original. So anyone who did integration for their what's it called? IA, right? Did you look up part and it was like, okay, there's definite intervals, so they have bounds and you have a specific area under the curve, but then there was something called indefinite intervals where you had to put on a plus C at the end?
Yeah.
So that plus C is saying that when you integrate or go backwards from taking the derivative, there is some family of functions that this guy's original belongs to, and then the plus C is kind of negligible because it disappears. So that's what the plus C is saying. It's saying, I know that it belongs to this family of functions, and it doesn't matter where I draw it because I don't have the specific bounds between which I've integrated. Okay? So that is why your sketch doesn't really matter, but it needs to have the key features in the right spot. Okay? Cool. cool. Let's go to, I don't want to confuse you. Let's erase all of this and leave that. Great. Too late. Already confused. Okay, let's go to number 4. Do you guys remember what it's called when a graph has pieces? What's his name? Piecewise. Okay, so this is going to take a little bit of thinking. What do you think the original is going to look like? Piecewise. Yeah. It's going to be a piecewise too, right?
Yeah.
Okay, cool. So let's consider each piece kind of discretely and put it on a number line and see where we land. All right, so F prime number line. While we don't have this guy equal to 0 at any spot, there is a problem on the graph. And it's standing out to us. Where is the problem happening?
At 1.
Yeah, it looks like it's kind of between 1 or 2, but let's pick and let's say it's 1. Okay, okay, great. What is happening at 1? I heard someone say it under their breath. It's yes. So the derivative is undefined, right? Yes. Okay. So the derivative is undefined when on the original curve you either have a cusp or an asymptote. Okay? Let's kind of figure out what this guy has. So, to the left of 1, what are the outputs of the first derivative? Negative. What about to the right? There you go. Okay, so how do you know whether it's going to be a cusp or an asymptote? Well, we are decreasing and then increasing. What does it look like we have at 1? A min, right? So, okay, I think it's going to be a sharp turn in the original function. Let's see where we land. Okay. So 1 is like my point of interest. I'm just going to put a little marker there so I know what to do. So to the left of 1, if I have a horizontal line as the graph of my derivative, you guys just did this, right? What did the original look like? It's like so much thinking and putting it all together, right?
A linear line
Uh-huh.
going down.
It's a linear function with a negative slope. Does it matter where these two pieces line up? No, they just need to match up at x equals 1. Okay? Then, to the right of 1, I have a line that's positive. What would its original look like? Quadratic, and it's what? Yeah, nice job. So look, okay, so we had a cusp at 1, or a sharp turn, right? Those are known as like sharp turns in the graph. And that's how we ended up having an undefined derivative. Because to the left there was a line, and then to the right there was a quadratic. It doesn't really look so hot, but maybe your picture looks better than mine. What about question 5? It's cubic. So its original is?
Nope.
It's the QU quartic. Yeah, there you go. So it's got 4. All right, you guys take a second on your paper and try to write the first derivative number line for graph 5. First find the zeros, then consider the signs.
So I say 2.
And if you're finished, do maxes and mins.
Okay. Max.
All right, guys, how'd you do? Looking good?
Next.
Okay, so you need a max at -3. You need a min at 0, and you need a max at 2. Does it matter exactly where you put them? No, you just need to have 2 highest points and then 1 in the middle, right? So a max at -3, a min at 0, and then a max at 2. And then we are increasing, decreasing, increasing, decreasing. I hope yours is a little more curvy than mine. They're not supposed to be like pointy like that. Here, let's do this. There you go. This is better. Okay. Yay! So, if you're given the graph of a derivative, what should you do right away? Draw it. Good job. On a number line. Then you can do what? Figure out maxes and mins, zeros, intervals of increase or decrease by the outputs of the derivative graph, and then you can sketch the original, okay? All right.
Do we need to do page 22?
What is page 22? That's notes. So if you're going back and like studying, you can go back and look at those notes. Right there? No. I mean, this was kind of what you guys talked about informally in your groups to take care of your sorting. This is notes if you're going back to study. And then this is what we're doing now. Okay? So, do you guys feel like you have a pretty good idea of what's being asked?
Yes.
Yeah? All right, let's try to move on to... Actually, this is good practice. We'll do activity 2. Let's do activity 2. So it says 6 graphs of functions are below, along with 6 graphs of derivatives. So the derivatives are on the back page, on page 24.
Wow, why would they do that?
Very annoying. I'm sorry. Yeah, who's they? Let's get them. All right, match the graph of each function with the graph of its derivative. Imagine the slope of the tangent line as you run your finger along the function. Make an interval number line for what f prime may look like, then match it to an f prime graph, okay? So, in the original graph here, f of x, this guy is what type of a function? He's linear. And what would his first derivative number line kind of look like? Let's envision the slopes of... It would be horizontal, and what kind of number would it be? Positive. Okay. So let's see if we can find that. A positive horizontal line. B and F. Let's narrow it down. Is it going to be B or F?
Which one?
B? Why do you say B? What does F have? Like a problem at 0, right? What? Yeah, it's undefined. It's got a problem at 0. So let's go with B. B looks
I
good.
say B.
Okay. Now, let's think about...
Two.
What do you think for 2? 2 is quadratic, right? It's giving D. Why do you think D would be that one?
Wow. I don't think you say that.
Well, let's think about the outputs of the first derivative, right? Positive. And then at 0, it changes to what? So it means on the original, we are increasing, then decreasing with our max at 0. You guys think it would be? Yeah? Cool. All right, keep going. Do you guys feel good like you can maybe do these?
Oh, what's
I got it. Is that F?
Yeah? What?
No. I think it's F.
No, 2 is D.
No, for 3.
Oh, 3. Ooh, think about it.
I did it. It hurts.
Think about it and run your finger along the tangent. Like, run your finger along. Yeah. It's A, right? Because look, what is this slope?
Oh, yeah.
Oh,
but it's negative.
Right, it's negative, then positive. So you're going to be looking for a horizontal line from negative, then positive. There's a curve or a sharp turn.
I knew I had a piecewise thing.
Good job. Anybody
So
else?
then
Not
that
sure
would be,
about
because
you?
that is
I
more
can't check your answers because I put them all in and I know your spot.
5 is.
I answered them.
Is one. I think you go.
Here, so I got
1B, yeah.
Where's the? Yeah, it is.
Yeah.
5 is
Yeah.
C. What do you mean E? There's no E.
5 is
E
C.
is 5.
And then 6 is E.
Yeah.
Done.
Right.
Lock it in.
6 is E.
B,
Yeah, makes sense.
D, A, F, C, E.
We got it right now.
I will fist you. So, you're gonna need a same piecewise thing at the same X. So it has to be
Why?
I'm looking here.
You need it.
No, what's so special for this? Look at the map.
No, but like this shows
Yeah.
piecewise this, so that and this one, when it goes to piecewise, it's going
Yeah, but look, there's no thing. There's no like open circle or piecewise at anything. I will fist at the same X.
We gotta stop.
But like, look, he keeps throwing paper at me. Like he wants me to bend him over.
Yeah, go beat his ass.
Go for it,
Jason.
Go get her. One.
All right, guys. Did you get them all right over here? Did I check them?
I got. Yeah, you checked us. We cool it.
Yeah.
Okay. So, good job, everybody. Here we go. Thank you. Okay. Let's answer some spooky questions about this. Are you ready? There we go.
This is like Scooby-Doo.
This is like Scooby-Doo. The following diagram shows part of the curve of a function f. Okay, so the diagram below is what? F or f prime or what?
Yes.
He is f. Do you want peas or carrots? Yes. Is f. So I'm going to label it f so I know exactly what I'm looking at, right? The points A, B, C, D, and E are on the curve. Great. B is a minimum. All right, I'm going to label this. D is a max. Okay. Complete the following table, noting whether f prime is positive, negative, or 0 at the given point. So I'm examining f prime. That means I'm examining what?
The derivative at a point.
Right. So I'm going to be looking at the slopes of the tangent lines and checking to see if they are what? I have to put a positive, negative, or 0 in the box. So I'm checking to see if the slopes of the tangent lines at specific points are positive, negative, or 0, right? Okay. So at A, draw a tangent line at A. What is the slope of that line going to be? Positive or negative? Negative. Good job. B, what is the slope of the tangent line at B? 0. Good job. What is the slope of the tangent line at E?
Negative.
Also negative.
Yay.
Complete the following table, noting whether f double prime. What is f double prime talking about again? What do we learn from f double prime?
It's the second derivative.
It's the second derivative, so it's going to tell us the what?
Points of inflection.
Points of inflection. What else?
There's not.
Concavity, right? Concave up or concave down. So remember, if something is concave up, what can it do? What is very special about it? What can it do? It can hold M&Ms. What if it's concave down? It cannot hold M&Ms. What about where the graph changes concavity? That's where it goes from being able to hold M&Ms to not being able to hold M&Ms, right? It is a point of inflection. Very good. And it's usually going to change about halfway between. So maybe like here, right? Is there another point of inflection on here? There could be another one over here, but I have no idea what the graph is doing past here. So I'm just going to determine that this whole piece over here is going to be concave down because that's where the graph stops. Okay? So let's examine what's going on here. At A, what is A? Can I hold M&Ms at A?
What?
Can I hold M&Ms at A? Yeah, he's concave up, right?
Yeah, dog.
Yeah. What about at C? Can I still hold those M&Ms at C? Yeah, we're not at the POI yet, right? That's where it was.
Oh, that's a POI. Okay.
Wait, so he's plus, okay. And then what about E? E is concave down. The M&Ms are falling out. This was our guessed POI, okay? All right. Let's keep cranking. I think we should do, let's do, I feel like these, we've all kind of done these. Let's go to, you guys want to do question 8? Yeah, let's do 8.
Yay!
Okay. It looks like it's a ton of work, but it's literally 8 questions, and we already did some of them, right? So each question is just on the big paper. Okay. 8a, it says let f of x equal 1/3 x cubed plus x squared minus 15x plus 17. Find f prime of x. What do you think you should do? Find the first derivative. Go ahead, my dearest friends. Yeah, that was easy.
That was mad easy.
All right,
2 marks already.
2 marks. B, the graph of f, so now we're talking about the original again, right? It has horizontal tangents at the points where x equals a and x equals b. A is less than b. Find the value of a and the value of b. So you know that horizontal tangents occur when what is set equal to 0?
The first derivative.
The first derivative. So let's set the first derivative equal to 0. Find those critical points. See what's up. So I've got x squared plus 2x minus 15. Set it equal to 0 and go ahead. Do we have to classify them at this point or just... We don't have to classify them as maxes and mins, do we? X equals A, X equals B. A is less than B. Okay, so A is -5. B is 3. Yeah.
Yep.
Now I feel like we have to do more. Let's see. Sketch the graph of the derivative. Okay. Well, you already have some pretty key information about it, right?
Yeah.
You know where its zeros are.
Yeah.
Or wait, no, that's the graph of, yep, we know where its horizontal tangents on the original are occurring, right? So let's go ahead and translate those into a number line and see what we're working with. So, on the first derivative number line, I have 2 critical points. They are what and what? What are they? Did you just say it? -5 and 3. Okay. And then now what do you think we should do for the sign below -5? Plug it into what? Factored form of the derivative. Beautiful. Okay. So let's do, can we use our calculator on this? Somebody look on the previous page, or the top of the page.
It doesn't say no.
It doesn't say no. All right. For the purposes of quickness, let's go ahead and test these in our derivative, in our calculator, or you can do it in factored form. All right, so
Positive, negative, and positive.
like it should, but I guess I didn't put it in there, so it's fine. So this would be positive, 0 is negative.
No.
Wait, where do you plug it into?
Factored form of the first derivative, because then you can do it real fast.
But I'm not.
Because look, this is the first derivative number line. It tells you what to plug it in. So you're like, okay, I'm working with the first derivative number line, so I'm going to test in the first derivative. Use factored form because it's faster. Like we did it without even doing a calculator because it's faster that way. So, what do we got? So we've got positive, negative, and positive. So remember, we're trying to sketch the graph of the first derivative, right? When we're sketching a graph of the first derivative, we've done sketching the original from the first derivative number line. We did that a few times already today. We have not done this yet, where we're sketching the graph of the derivative. So let's look. They don't give us the original, do they? But they tell us that it is what type of a function. What's the original? Cubic. So that means your derivative has to be what?
Quadratic.
Quadratic. And we have the zeros already written out for us, right? They are -5 and 3. So we could get a pretty good sketch of this thing going, right? It's quadratic. It's got zeros at -5 and 3. Huh? On the original it would be, but we're sketching the derivative. So on the original in the cubic, there would be a max there and there would be a min at 3. But we're sketching the graph of the derivative. So we're sketching the quadratic that comes from this information here, right? So what were we looking at earlier? We were like, okay, so the outputs of the function to the left of -5 were positive. The outputs of the first derivative to the right of 3 were positive. And then we looked at the outputs of the derivative between those two and they were negative. Do you see how we like are working backwards kind of from what we were doing earlier? Okay, so now we're generating the graph instead of just highlighting it. So this would just be a quadratic that looks like that. Okay. I feel like everyone's fine going the other way, and then this way they're like, what? All right. Hence explain why the graph of f has a local maximum point at x equals a. This is why we love a first derivative number line. We don't have to explain anything really because we just illustrated it up above. We just have one nice little sentence telling us what's going on, okay? So we can say the sine of the first derivative, and we're talking about a. A was which one? A was equal to -5, so this is A. Okay, the sign of the first derivative changes from positive to negative at x equals A. Therefore, there is a max at x equals A. There shouldn't really be a period there. There we go.
Therefore, what?
There'd be a max at x equals.
There is a.
There be a max.
I put a period there, and then I changed my mind. Okay. So that's our answer there. Perfect. 8E says find f double prime of b. Find me b. Look on the paper. Find me b. B is what?
3.
Okay. What's f double prime? Do we have it yet?
No.
Can we find it? Yes. Let's do it. Where is it? X squared plus 2x minus 15.
Find addition in my collection.
Okay, so I got 2x plus 2. What am I doing with b is 3 now? That's going in for, okay. What? Why are the bodies hitting the floor? What is everyone doing? The bodies hit the floor. Is that it? Yeah. Okay. Hence, what? That's it. Yeah. Hence, use your answer to part DI to show that the graph of f has a local minimum point at x equals b. Okay. So use your answer to part DI. Where's DI? Oh, nothing. It's literally the same, and it's not split up with an I, so perfect. So we would just say the graph of f has a local minimum at point x equals b, and then it's the same exact thing that you wrote up. I was going to say upstairs.
What's that say?
Relative and local mean the same thing. So you have absolute global, and then you have relative local. They are lumped together.
So, relative, I meant, so, local is 1 point.
Min.
Look,
Fence.
absolute only occurs on a closed interval. So if you are like from 0 to 10, then you can identify the absolute max or min because you know where the graph starts and stops. But in this case, these are just like general functions like f of x, right? So he has arrows on the end, so we can't really identify them. So we would just say they're saying a local min, but we're just like, it's a min, you know? So the graph of f has a local min at the point x equals b because, what did you guys write here? What are some good answers? What did you write?
What?
Because the sign changes from negative to positive.
Yay! Changes from, so a min, it's going to change from negative to positive. Okay. All right, here we are. This is the end cap. This is the 5 marker at the end, right? So you're probably going to have to use your what?
Brain.
Your left leg, your brain. Good job. So it says the normal, at least one finger. 1, 2. The normal to the graph of f at x equals a and the tangent to the graph of f at x equals b intersect at the point PQ. Find the... Wow! Find the value of P and the value of Q. For those at home, just thank goodness you're not here. It's no good. All right. So what was the original? What type of a function was the original? What type of a function was the original? It was a cubic, right? Does anyone have any idea what it looks like? Not really. So let's just draw a cubic. How does that sound? You do know. What do you know? Yes, what do you know?
Negative 5 to math.
Heck yeah. And then what is a min? Okay, cool. So it says the normal to the graph of f at x equals a. Which one was a? Ooh. B is 3, a is negative 5. Okay. So this is a. And this is b. Okay. The normal to the graph of f at x equals a. What would that look like? The normal to the graph of f at x equals a. Well, first let's draw the tangent, right? And then we'll figure it out from there. This is the tangent. So what's the normal look like then? This was from your test, right? What's the normal look like?
Zero.
It's got to be a perpendicular line. And that perpendicular line passes through what x coordinate?
5.
Negative 5. So how do you write the equation of a vertical line that passes through negative 5? X equals negative 5. Good job. Okay. So this is, let's just label this because this diagram is already insane. Okay, norm. That's a norm. There he is. Now what? And the tangent to the graph of f at x equals b. Okay, so same thing. Let's do it again. This is the tangent. And then the tangent. This is not the normal. We're just looking at the tangent. Okay, cool. So the tangent to the graph of f at x equals b intersects at the point PQ. Okay, so we're looking for where this guy intersects. Oh, that's way too thick. You can't even see what I'm writing. Come on. Guys, can you figure this out faster than I can because my computer's being really slow?
Stop. If you're going to do that, you are disgraceful.
First of all, PQ is happening here, right? P is the x coordinate, negative 5, and then Q's what?
Y.
What do you have to do? Plug it in. What are you going to plug in? To the regular F. Ooh, alrighty. Can you guys read me the equation in the original?
1/3 x to the 3 plus x squared minus 15x plus 17.
Okay, and we have to evaluate it for 3? All right, that's fine.
I got negative 10. Nerd.
Our sketch does not match this, does it? Let's see. Let's confirm first. So we got 1 plus 9 minus 15 times 3 is 45 plus 17. So we got 10 minus 45.
Where are you?
Oh,
Huh?
I got a blind. I'm blind. I got scissors.
Wait, what?
I think I put it in right.
What happened? What'd you do?
I don't know.
It's 3 to the 3. Not 3.
Oh, hello. Hello. Wait, so
That's
3 to the
7.
3 is
So that's
29.
9 plus 9.
So then, what are we going to get here?
Something.
Well, this is going to change now. 18 guys, I'm so brain dead right now. You have to do this for me. 18 minus 45. What do I got? Plus 17. What?
27.
Plus
Negative
17
27.
is negative 10.
Negative 10? Woo! Okay. All right. Find the value of P and the value of Q. And then what's Q?
Negative 10.
All right. Now you guys can just start work. Oh, it's the end. Bye.